Welcome everyone to today's seminar co-hosted by CATCH and SOLAS Early Career. Okay, so to start with, I think we will have a brief introductions to introduce SOLAS and also CATCH, and then we'll have the talks by the two speakers. Okay, and okay, so I will just have a quick intro on the SOLAS recent activities. Okay, all right. Yeah, I would like to introduce myself. Okay, I'm Tham. I'm currently affiliated to Yat-sen University in Zhuhai, China, and I'm one of the SOLAS Early Career Committee right now. So it's great to share what SOLAS is doing right now. Okay. So as you know that SOLAS, we have 5 core teams, which is included the greenhouse gases, ocean AC interface, and the atmospheric deposition interconnection between aerosol clouds, and the team 5 is on the ocean biochemical controls on the atmospheric chemistry. And we also have this cross-cutting teams, which integrate this upwelling system, polar oceans and Indian Oceans. And then we have climate interventions and also science and society. And currently the co-chairs are Krista and Bill. And then we have 2 IPO. One is located in Galway in Ireland, and then the other is in Xiamen, China. And these are some SOLAS overview activities right now. And then in the recent years, between like 2020 and 2023, okay, we have several new activities and initiatives. Okay. One of these is we have established this Early Career Scientist Committee, which is launched in January 2025. And then we have this new panel to promote the ocean atmospheric couple research at regional scale, including Southeast Asia and Latin America. And then we have eddy coherence initiative, fire initiative, climate interventions, and SOLAS modeling initiative, and also special features in this elemental science of Anthropocenes. Okay, and the most important part is that in this November, okay, the SOLAS will organize this SOLAS Open Oceans conference in Goa, India, and you are still welcome to submit your abstract and discussions, and the deadline will be on the 1st of May. And if you have some abstract to submit, please do it so as soon as possible. You're welcome to join us in India. Okay. And recently the SOLAS will have also like working on this new SOLAS science plan, which included from 2026 to 2035. And this is the new look of SOLAS science plan. Okay, and then if you would like to know more about SOLAS, please join our mailing list for more information. And then yeah, thank you. And then hand it to you to Hélène.
Can you see my slides?
Yes.
Yeah, okay. So welcome everyone to this CATCH SOLAS seminar. So my name is Hélène Angot. I'm a CNRS research scientist based in Grenoble in the French Alps. And I'm part of the organizing team for the CATCH seminar series. If you want to learn more about the CATCH activities, you can check our website, join the mailing list. I'll keep it very brief, but basically CATCH mission is to facilitate atmospheric chemistry research in cold regions of the Earth. So by the cryosphere, we mean all regions that are seasonally or permanently covered by snow and ice. So that includes polar regions as well as high mountains or high latitude urban cities in wintertime. So without further ado, I'd like to introduce our speakers. So first of all, we'll have a talk by Anoop Mahajan. He's based at the Indian Institute of Tropical Meteorology. And then we'll have, just after his talk, we'll have a short Q&A session directly related to what he talked about. And then we'll have the second talk by Xu-Cheng He. He has a double affiliation at the University of Cambridge in the UK and the University of Helsinki in Finland. Similarly, just after this talk, we'll have a short Q&A session, and then we'll move on to an open discussion on the topic. So I'll stop sharing my slide. Anoop, if you want to go ahead, the floor is yours.
Thank you. Let me quickly share my slides. Hopefully you can see this and also see it in full screen.
Perfect.
Excellent. Okay, first of all, thank you for inviting me on this forum. It's always nice to see some familiar faces and talk about iodine. You know, iodine, as we were joking earlier, is a very sticky substance. I started doing some work on it during my master's, and here I am 20 years later still doing the same thing, right? But my plan for this this talk is mainly to focus on the gas phase species of iodine, what kind of observations have taken place, what are the kind of impacts we are looking at. I'm not going to go too much into the production, the emission side of things, because there are much better people to talk about it, and I'm obviously not working as much on that aspect as the others. And then, of course, then Lance is going to take over, and he's going to talk a little bit about the aerosol side of things. So I'll stick to the gas phase species. Just to give you a little bit of the history, iodine is actually not that new in terms of the interest in it. There have been observations of iodine going on for more than 60 years. The initial organic compounds, they was being measured early in the 1970s. James Lovelock had done this, this long measurement across different places in the Atlantic, Pacific, etc., where they measured some of the iodine organic compounds for the first time. And ever since, there have been a lot more measurements that have been happening across the world. Iodine in aerosols has also been measured for a very long time, since the 1960s, and it's been measured pretty much in every ecosystem that you can think about, all parts of the environment. There has been some iodine in the aerosols, which is not completely unexpected. And then the idea that inorganic iodine emissions also play a bit of a role from the ocean surface into the atmosphere was also proposed in the 1960s. But of course, proposing is one thing, and then actually getting numbers on it is another thing altogether, which has been happening over the last few years. And quite a few people who are here in the audience have worked a lot on this. So these are just some papers. So the evaporation of iodine from the ocean was suggested, as early as 1963, and they had come up with a rate which they estimated for the entire ocean surface. Then Bob Deuce did some observations of iodine and bromine in aerosols, and they saw that there was quite a lot of iodine in the aerosols, and it was actually increased from the seawater content. But the first idea of its bigger role in tropospheric photochemistry was proposed by Chamadiz and Davis. And they basically said that, yes, it should affect the ozone, NOx, and HOX system. Of course, the kinetics were not very well known back then, so it wasn't possible for them to quantify the total impact, but they at least saw the potential of it. And of course, the idea that inorganic iodine could be emitted was also proposed quite early on, and they were not entirely sure what the process would be, how much of it would come out. They essentially just said it is some kind of iodine compound, most probably I2, etc. So all these ideas were there for a fairly long time. And then it went into a bit of a lull. Observations of organic iodine and iodine in aerosols were still going on, but not too many observations were forthcoming about the reactive side of things. And this all suddenly changed in the late 90s and early 2000s. There was a lot of interest in iodine chemistry that developed, mainly because of some really seminal papers which came out. So, for example, the first detection of iodine oxide in the atmosphere was done in 1999, which showed that, yes, it can play a reactive role in the atmosphere itself. Then, in addition to iodine oxide, I2 was first measured, and this was measured from at Macehead, where several campaigns have taken place focused on iodine chemistry, and it showed the presence of iodine molecules, so a very large source of iodine, and this was from seaweed, so it had a very strong tidal signature. And then, of course, groups around the world, including Gordon McFiggin's, Jimenez, Colin O'Dowd's, etc., they did a lot of observations on the iodine oxide particles, which were also observed whenever you had these peaks of iodine from your seaweed coming out. So this really sparked a lot of interest in iodine chemistry again, and talking about its role in the global atmosphere. But that was still thought to be very regional, very specific towards seaweed emissions. But then suddenly things started changing a little bit more with the detection of iodine oxide in the polar regions. And this was a paper by Alfonso Saez Lopez, where we did observations of iodine and bromine compounds across an entire year at Halliway, the British Antarctic Survey Station. And basically what it showed was iodine and bromine were available in similar concentrations and with a very large peak during springtime. So since the role of bromine on ozone depletion was fairly well known by this point, there was a lot of interest because it just showed that it's not just bromine, but also iodine, which can play a fairly large role. And these levels were the highest that have been measured anywhere outside these seaweed regions. So obviously it showed that it could have a massive impact on not just local, but maybe regional atmospheric chemistry also. This was followed by some observations that we did with the group in York, led by Lucy Carpenter. And what we did was we did some observations of iodine oxide at Cape Verde, which is in the Atlantic. And what we saw was iodine was essentially present almost all the time, ubiquitously throughout the year. And it wasn't present at levels seen in the Antarctic, but still significant enough levels. Together with bromine, it could lead to a depletion of almost 45% of the ozone. So suddenly this was very important because it showed that this could play a role on the global marine boundary layer and hence have an impact on global atmospheric chemistry rather than just regional. The other thing that this campaign led to was the group from York and Lucy's group was also doing observations of halocarbons. And basically, if we ran the model with halocarbons, it severely underestimated the iodine oxide concentrations. So it basically said that, yes, we do need another source of iodine into the atmosphere, which went back to this entire idea of Garland and Curtis talking about maybe there's an inorganic source of iodine happening. So basically what was being shown through these campaigns in the 2000s was, yes, iodine does play a role in the global atmospheric chemistry, but we are underestimating some of its sources. So that's where this was there. And then this was also followed up by extra campaigns that took place around the world. There was campaigns which took place on ships going across the world. There's this paper by Cristina Prados Roman, which talked about iodine chemistry on the global marine boundary layer through observations in different ocean basins, which showed that, yes, it's happening everywhere. It's not just restricted to one single island in the Atlantic. And then observations of iodine also were made in the free troposphere, and later on also the presence was shown in the stratosphere. So it showed that, yes, it does really impact the global atmospheric chemistry. But yeah, the question of course was, yes, where is this extra iodine coming from? But before that, we also did some observations or estimations to see whether it really does impact aerosol formation, because the process of formation of aerosols was at least thought to be well known at that point through these observations in Macehead and Brittany, etc., over the tidal regions. And yes, it was shown that, yes, you can form quite a lot of particles, and through whatever information we had back then through observations or lab experiments done by Colin O'Dowd's group, Jimenez's group, and John Plain's group, we basically came up with a parameterization relating iodine oxide concentrations to the number of particles. And what at least this showed back then, when the entire process was still not very well known, was that, yes, iodine oxide can play a pretty important role in new particle formation, but it would play an important role only when it has elevated concentrations, but not in the global marine boundary layer where the concentrations are pretty low, between 1 to 2 parts per trillion. So this was where things had been left back then. But we still didn't know much about its source, and this is when Lucy's group did some really interesting lab experiments, and they ended up identifying a mechanism through which ozone deposition on the seawater or ocean surface essentially leads to a sequence of reactions through which there's HOI, so hypoiodous acid, and I2, molecular iodine, which are emitted back into the atmosphere. Now, this was a really important paper because not only did it confirm some of the hypotheses and proposals by people back in the 60s, 70s, but also it gave us a rate that could be plugged into a model to try and estimate the impacts of it. And of course, this is in addition to your organic halogens, which there was sufficient observations to try and build an emission inventory. So this is what was done afterwards. Basically, all these emissions were put into a global model, and then the impacts on the global atmosphere were estimated. Of course, remember that this is back in 2012, and this was all very new. So there were some estimations, but it still wasn't very clear. It was done only in one single model, which needed to be introduced in other models also. So after Alfonso did some initial work on this, what they basically said was, yes, iodine plays a pretty important role in terms of determining the oxidation capacity of the entire atmosphere, and plays a much more important role in the troposphere as compared to your bromine and chlorine reactions, which gets reversed in the stratosphere, where bromine and chlorine reactions start to dominate over your iodine reactions, mainly because the concentrations of iodine are much smaller in the stratosphere as compared to the other two halogen compounds. But yes, in the troposphere, it does play a pretty important role, and also in the UTLS, or at least the upper troposphere, it plays a fairly important role. So this was followed up by Lucy's group also, along with Matt Evans and Thomas Sherwin, introducing halogen chemistry into the Geosciences model, which also showed that, yes, it does affect ozone concentrations. It affects the HOX concentrations, the NOx concentrations, and the sulfur dioxide concentrations. So suddenly, from going and talking about iodine chemistry in terms of being important only over tidal regions, the sequence of studies which happened essentially over a decade or so showed that, yes, it has a global role to play. And this role cannot be ignored completely if you want to get your ozone budget right in your models. And then this was also followed up with other studies in terms of air quality implications. So basically what happened was, after doing the global modeling, these halogen chemistry was introduced into your regional models, which showed that, yes, regionally it can affect ozone concentrations on considerable levels. So for example, as much as 60% of ozone depletion in certain parts of the environment can be caused because of halogen chemistry. This was shown not just over the oceanic regions, like over here by Badia Alba's study in 2019, but also over the continental regions, where it's not just your emissions from the oceans, but even your anthropogenic emissions of iodine compounds end up playing a role, and they can affect air quality over the continents also. We also did some studies on this over the Indian region, which was basically, we did a sequence of cruises. Over here, we measured the amount of iodine, the amount of iodate and iodide in the sea waters, which was done by Rosie and Lizelet, who had come on those cruises also. And what we basically showed was, yes, we can estimate the total emissions of your hyperiodous acid and molecular iodine using your iodide and iodate and your ozone concentrations, because there was a parameterization that Lucy's group had developed. And what we can see is that, yes, as you go closer to the continents, there's a large amount of emission. This large amount of emission obviously has implications on your air quality. So over here, we see the difference in ozone. As much as 25% of ozone depletion can be caused because of iodine compounds in this case. So regionally, obviously, it was very important, but also it showed the really interesting interplay between anthropogenic emissions and your natural emissions because of your ozone deposition or on seawater, leading to iodine emissions. So what you see is the red dots over here show your iodine compounds as your iodine oxide in the atmosphere, and you can see that they keep increasing with ozone up to a certain point, after which they become disconnected, even though your emissions are still connected to your ozone, because that's a very straightforward linear emission. But the disconnect happens because of titration because of nitrogen oxides. Nitrogen dioxide reacts with your IO to give you IONO2, and that becomes your reservoir species. So ironically, there was this interplay where you have an increase in emissions, but the decrease in the impacts because of anthropogenic emissions. So all of this chemistry obviously was very interesting. But also, there was an obvious question to answer considering the role of ozone deposition on iodine emissions. So basically, this was the hypothesis by Lucy's group, which basically said ozone deposits, and then you have hyperiodous acid and I2 basically coming out into the gas phase, and that would of course lead to ozone depletion. So it's some kind of a feedback control on ozone concentrations that's happening because of this feedback of iodine coming out from the ocean surface. The question, of course, was what happens if you increase your ozone concentrations? Because as we know, your tropospheric ozone concentrations have increased by almost 50% globally. So all this extra ozone that is being produced by anthropogenic activities would also deposit onto the ocean surface, and then that would lead to further emissions of HO and I2. So there's this potential amplification of emissions of iodine compounds, which could take place mainly because of the role that deposition of ozone has. So of course, we had to try and estimate what this does and to check whether that is really true. The first indication of this playing a role in terms of actually an observable role came from these two papers which came out in 2018. One was by Carlos Cuevas and the other one was by Legrand. And what they did was they went and made observations of iodine in ice cores, and both of them were ice cores and tree rings. And basically what both of them saw was there was a definite increase in the amount of iodine in their samples from the advent of the Industrial Revolution, or since ozone concentrations really started increasing. So this basically was like a smoking gun approach. It's talking about, yes, this can definitely have an impact, and it is an observable impact, which makes things a lot more interesting, because that basically means that the future emissions of iodine compounds are not the same as in the present or in the past, and that can have climatic effects. So we wanted to know whether there is further proof to this. So what we did was we did some observations of iodine in the Arctic, and it's a very interesting sequence of events in terms of measuring iodine compounds in the Arctic. One thing you should remember is iodine was observed in the Arctic aerosols well into the past. So if I remember, there was this paper by Bill Sturgis back in the 90s, which had measured iodine across the entire across several places in the Arctic, and they had showed that yes, it is present in the aerosols, but gas phase was not really observed, so it was thought that it's not very important at all. So Tuckerman et al. In 1997 went and did some observations, and they basically saw that IO is not detected, and they had a pretty good detection limit of about 1 parts per trillion. So the reactive chemistry is obviously not as significant as in the Antarctic. Remember, in the Antarctic, we had observed concentrations going up to about 20 parts per trillion. So obviously, there's a big difference between the Arctic and Antarctic, and that is fairly well understood, or at least thought to be understood. There are some hypotheses which the models are able to replicate this difference with. But basically, the Arctic, you could not observe it. And then basically after that, in the early 2000s, the groups from Bremen and from Heidelberg also went there and made observations of iodine oxide in the column. So these were full column observations instead of just surface observations. And they said, yes, there might be there was some hint of it, but it wasn't a regular detection at all. Then in 2005, Lucy's group had initiated this project called Cobra. We went as a, sorry, no, this was before Cobra. Lucy's group had went and made some observations of hydrocarbons in the Arctic air, and they also said that it could lead to almost 1 part per trillion of iodine oxide in the Arctic atmosphere. And then finally, in 2010, as a part of the Cobra expedition, we went along with Lucy's group, and we made observations of iodine oxide using a long path DOAS instrument. And what we saw was concentrations peaking at about 3.2 parts per trillion. So that was much higher than most other groups had observed. But there was a caveat to it. It wasn't being observed all the time. It was observed only when the air masses were passing over these open water areas called polynyas. So there was obviously some sea-air exchange, which was introducing all this iodine in the atmosphere. At that point, we did some modeling studies, and what we thought was it's actually organic iodine which is contributing to it, and we did not feel the need to invoke and inorganic source at that point, at least. But then a couple of years later, Andrea went and made some observations of I2 in the Arctic and showed that there was a significant snowpack source of I2, which is possible in the Arctic itself. So there was this steady progression showing that there was hardly any iodine, and there was more and more iodine coming out through different sources. And then a couple of years ago, we participated in the Mosaic cruise and made observations of iodine oxide through the entire expedition. And we basically were able to measure iodine oxide pretty much all throughout the campaign, with peaks of about 3 parts per trillion. And this was pretty interesting, mainly because we knew that the big ozone depletion events, which can be seen on the top panel over here on the left-hand side, they coincided with your big bromine oxide peaks. So most of the ozone depletion events were being dominated by bromine chemistry, but iodine chemistry definitely played a role in them. But besides playing a role in the springtime ozone depletion, there was a steady amount of iodine oxide throughout the entire year. The levels were pretty low, as low as 0.3 parts per trillion at certain times, but they were detectable. So basically what this showed was significant ozone depletion is happening, but that is mostly because of bromine-dominated chemistry with the contribution of iodine chemistry. Bromine is observed only during the springtime. We understand that chemistry a lot better than for iodine. Iodine is observed through the entire year, which brought in the question saying that how much of a contribution does it have in terms of the total oxidizing capacity of the atmosphere. And we ran the model on all the days that we had observations, and what we basically showed was most of the loss of ozone is obviously going to be because of the photolysis loss. That's not surprising, especially in summertime, etc. It's going to dominate. Then you have your bromine-led losses, which play a pretty big role in your springtime. And then you have your iodine losses, which play a role in the springtime also, but also throughout the year. So iodine also enhances the depletion of ozone through cross reactions with bromine, etc. And then if you put the numbers together, then throughout the year, iodine actually leads to more ozone loss as compared to bromine, or at least comparable. So it's a pretty significant loss of ozone in the Arctic atmosphere also, something that we think has changed over time. Of course, we don't have enough information going back into the past, whether the concentrations were just below the detection limit or they were just were not there. Because remember, as I said, in the springtime, we do see levels going up to about 3 ppt or so, but the rest of the year, the levels are below 0.5 ppt or so. So it's fairly low concentrations, which is why people in the past maybe have not been able to observe it because their detection limits were around a ppt or more. So it's possible that it was playing a role earlier also, but we can definitely ascertain what role it's playing now. Then considering this and considering that there was this amplification of emissions that was not just postulated, but also there was some evidence for it through ice core observations and also through the Arctic. The question, of course, was what happens if we do this on a global scale? So Alfonso's group and I, what we essentially did was we included all the known observations, emissions of halogen compounds into a global chemistry climate model, and we tried to estimate what is the radiative impact of it. So does it matter only for interesting atmospheric chemistry, which some of us love, but does it really matter for the climate also, is the question we wanted to answer. And the way we thought is the way it's going to affect climate is through secondary effects, not through direct effects. The first one is ozone destruction. Ozone is a greenhouse gas. So if you're reducing it, you affect the radiative forcing. Then because of the impacts on methane, this is not iodine dominated. This is more chlorine dominated. But if you have an increase in chlorine emissions, what you have is a reduction in methane lifetime. But iodine can affect this in a contrary way. It changes the Hawkes concentration. So it actually reduces your OH concentrations, by which the methane lifetime can increase. And then, of course, there's aerosol formation. Whatever was the state of the knowledge back then, well, back then as in a couple of years back, we put it into the models and we tried to estimate its effect on aerosol formation also. And the kind of sources we included was anthropogenic, which is fairly small. Then, of course, seawater emissions of organic iodine and inorganic iodine, then sea ice emissions for which we had parameterizations that were developed. And what we got were numbers essentially saying that the total effect of all halogens together is about 0.13 watts per square meter. The impact of iodine is about half of that. And the way it affects this is basically by reducing ozone through ozone depletion reactions, which are very well known, increasing the amount of aerosols, and then you also have your effect on methane, which is a secondary effect because of Hawk's reduction itself. And then, of course, this because these are organic iodines or organic halogens which are emitted, they can also lead to an increase in stratospheric water vapor. But you put all of that together and it's a net cooling effect. So it basically showed that, yes, in addition to just affecting the oxidizing capacity and affecting interesting chemical reactions, what it can affect is the radiation also. But that was not the only point. The point was to check whether this is changing over time, which is what would be of interest for climate models. And this is basically a feedback in two ways. One is direct anthropogenic emissions, and the other one, which is the clear side of the bars, is the amplification because of anthropogenic emissions. So ozone amplification leads to deposition on seawater, and that leads to more emission of these compounds. So there is, as you can see, at the present day, we have this number because of different types of effects. That's about 0.13 cumulatively. And then depending on the future scenario you use, the change is as shown and is very different from your present day itself. So if you have a lot of ozone over there, you would still end up emitting a lot more halogen compounds. If you do reduce your ozone emissions or ozone formation in the future through reductions in NOx, etc., then you would have a lower impact of halogens on the total radiative forcing. So this is basically where we are at right now. We have some estimates of this. Remember that this is super exciting, of course, but it's just one model. So we still need to run this in multiple models to be able to get better uncertainties or better idea of what these numbers mean and whether they're accurate also. So in terms of the future questions, where are we heading towards now? We are heading towards, these are the main questions, at least according to me, and I'm sure everybody has more ideas about this. First and foremost, we do need more observations, and we need more observations not just of I2 or HOI and IO, which we have been measuring for some time, and there is a steady data set building, but we also need to measure some other iodine compounds, especially if we can start measuring the nitrates, etc. We might find out some pretty interesting things happening higher up in the atmosphere. The second part is the heterogeneous chemistry is still extremely uncertain. How much of it gets recycled, how it gets recycled, what are the photolysis rates within aerosols, whether they contribute to its re-emission. These are big questions, and this personally I think is a big a question we really need to sort out, because quite a bit of the heterogeneous chemistry tends to happen not just in the marine boundary layer, but also in these places with deep convection through which all these compounds get into the stratosphere. And how much of an impact it has on the stratosphere. I mean, we know for sure now that iodine does affect the stratospheric ozone. Whether that's going to change over time is the uncertainty comes because of heterogeneous chemistry. So we definitely need some laboratory work on this. The third and one of the biggest uncertainties, although we do have some emissions now, is do we really understand the emissions properly? So one of the studies we did in the Indian Ocean, which I showed you, the impact of ozone on air quality, or impact of iodine on air quality in the Indian region. For that, we found something pretty interesting, saying that if we put the same parameterizations as we have used in the models right now for emissions of iodine compounds, especially the inorganic iodine compounds, then the model overestimates the atmospheric iodine content by as much as 40%. So we had to drop down the emissions of iodine according to the parameterization, which is from Lucy's paper and all. So obviously there is something happening. We did have observations of iodide, so that's not the uncertainty. It's the CF flux, which is changed, which is different. And whether this is because of the role of SML, which kind of inhibits the emission, is something that I know, Rosie, Lucy, Ryan, they are all working on. And I think that's really going to help improve estimation of the emissions that are happening. happening. In addition to this oceanic emissions, there are some uncertainties on anthropogenic emissions of these compounds, which are starting to be used more and more in industries. So that's another aspect we really need to sort out. And then the final big unknown is also what is the actual contribution to aerosol formation and growth. There are questions which remain about the underlying processes, and the next talk is going to cover quite a few of these things. At least the estimates that we had made back in 2010 showed that it really does not matter on a global scale. It could matter on local and regional scales, but lots of new experiments have taken place, and there's a better understanding on the processes behind it, which we'll talk during the next talk and hopefully get an idea of where we are in that turn. With that, I'll stop my talk. Hopefully it was just in time, and I'm happy to answer any questions or discuss.
Thank you so much, Anoop, for this fantastic overview of iodine chemistry. One of my questions was actually, what are the remaining gaps in our understanding of gas phase iodine chemistry? So your last slide is just fantastic because it's a perfect summary. It answers my question. Do we have questions in the audience before we move on to the next speaker? Yeah, Lucy, go ahead.
Walk through iodine history, which I really enjoyed. So thanks for that. I mean, you've now got quite a few more observations in the Arctic of iodine. What kind of clues are this giving us? It feels like we're still not really sure about what's going on in terms of the sources. Do you have an idea through sort of spatial heterogeneity? I mean, we focused on these polynyas to start with. Is that still your thinking, or do you have hints that something else is going on now?
So during the Mosaic expedition, we saw it pretty much all the time. We tried to do the back trajectory analysis, and we saw that there was enough iodine even in air masses which hadn't been exposed to polynyas in days at times. So obviously there's some other source which is playing a role. Andrea has done some estimations about maybe there's a snowpack source, how active it is it a primary source, is it a secondary source? There are question marks about that. Of course, the sea ice amount is reducing, so whether the ozone deposition is playing more of a role, that's also a question. So I guess what I'm trying to say is I don't know, but yeah, we definitely we do need more observations, because it's the first time that we've observed iodine almost on a continuous basis in the Arctic. Otherwise, it was always snapshots, sometime or the other we were seeing it. So, but the fact that we are starting to see it more and more, and the fact that our detection limits are now much lower than they were 10 years ago, so more observations will help. We have set up some instruments in the Arctic right now, and we've been observing things over the last 1 year, well, 6 months now, and hopefully my new student is going to analyze that data. So maybe we'll have an idea from that. But yeah, I think it's a good time to think about an iodine project in the Arctic, concentrated project on iodine chemistry, maybe as a part of the upcoming IPY, or you've organized some good expeditions in the past. Maybe it's time to do that.
Good hint, Anoop. We'll chat on that one. Thank you.
Sure.
Rosie, go ahead, please.
Yeah, no, thank you, Anoop. That was really, a great summary of iodine and like the progress in it, which is really good. And I agree entirely. I think there's a lot to be done in the Arctic, and on the water side phase, it had been very uncertain. All the parameterizations that we've used for sea surface iodide, I think, are based on 0 observations of seawater iodide, and now we have some more. But my question is actually probably a much more simple one. You mentioned a few times about anthropogenic halogen emissions, and I just wondered, it's not something I know much about, what are the dominant anthropogenic sources for iodine, and are they likely to increase or decrease in future?
Yeah, so there is some industrial use of these compounds, which is contributing to things. It's for iodine, it's not a dominant source. Your dominant sources are your natural ones. You get more of the other halogenated compounds which come out. One of the things which is changing is there's a lot of seaweed cultivation going on. So, that's contributing to a source of things. Until now, most of the studies on the seaweed cultivation have been focusing on bromoform, but not on the iodine compounds. If there are lots of uncertainties on this, depends on the species that you use, etc. But we've got some estimations of this. If we continue on the path of saying that seaweed is an answer for carbon sequestration, the total amount of iodine that might be emitted might be significant. It still won't dominate over your natural sources, but it will start becoming significant at least on regional scales. So, that is a very potential source that we are looking at right now. There's still a lot of uncertainty. We don't have good quantification on it, but we are working on it. Yeah, but plus, I don't know. I mean, one of the other things I keep thinking about is, the work you guys are doing on the SML, the secondary effects of how the SML is changing because of anthropogenic, emissions. That is going to change this entire natural source which is coming out, and I don't think there's enough information or enough experiments that have been done to identify how much of a role that has. Hopefully, you guys can give us an answer soon.
We live in hope.
I do have a pretty naive question, Anoop. So you mentioned differences in IO concentrations over the Antarctic compared to the Arctic. Could you summarize the main drivers of this difference?
Yeah, I mean, again, this is one of those things which has been hypothesized, and it's been put into models. Parameterizations have been done. How much of a direct proof there is, yeah, that's another question. But the hypothesis, at least, the one which Alfonso came up with, was it's got to do with the thickness of the sea ice. How the saline, the saline waters, etc., transfer through it. It's got to do with the biology over there in the Antarctic. There's a little more active biology. The type of species, etc., are a little higher in the Antarctic as compared to the Arctic. So all of these things combine together and lead to an emission of iodine, which is much more potent in the Antarctic as compared to the Arctic. One thing to note is it's not as if the entire Antarctic emits a very high amount of iodine either, right? So most of most coastal Antarctica has similar emissions as the Arctic. It's just there are some areas which are highly concentrated, especially around the Weddell Sea and all, where you have this thickness of sea ice, you just have the right conditions for the biology, etc. That's where you end up getting a lot more emissions. But for example, we did some observations on the eastern Antarctic side, which is where the Indian stations are, which is pretty much straight down from South Africa and straight down from Pakistan. And over there, we see levels which are very similar to the Arctic. So you don't see these 20 ppts, etc. So just the conditions are right in certain parts of Antarctica. Of course, the question also is how that's going to change in the future, because the sea ice conditions, etc., are changing drastically in the Antarctic. So that's something that we still haven't run in the model. I know we are doing some polar modeling work on this, but there's a lot of uncertainty on how that will change in the future.
Thank you so much. Someone else has a question, so I'll shut up. Christina, go ahead.
Hi to everyone. I'm Cristina Roman from Spain. Hi, Anoop. Nice to see you. Nice to see you all, because I've seen you from your names on the papers, but it's great to see your faces now here. More than a question, it's actually a comment to this point that you're mentioning regarding Antarctica. I know we already know, but at INTA, we are currently doing long-term observations from Antarctica with TOA. So that means VRO and IO. And we have a station located in the southern part of the Weddell Sea and in the northern part of the Antarctic Peninsula. That means Belgrano and Marambio. And we have 8 years of data for now. So we are still working on that. Actually, this work is mainly led by my colleague, Olga Puentedura, and we haven't seen 20 ppts at any moment.
So what is the level you've seen?
Actually, we are surprised. We are quite surprised that we haven't seen huge amounts. We are talking about a median, at a mean 5 ppts or something like that.
Right.
We do see more iodine IO in Belgrano, which is expected, but not as much as the satellite said, by the way.
Right.
We have not seen this hot spot that is supposed to be on the Weddell Sea. Then again, it will be also related to the back trajectories and all that. So we are working on that. Also, we will work on the relation to the sea ice type. But we are surprised that we haven't seen this huge peaks that sometimes you see. Again, we are not through the ice, we are located on the ground, but at Marambio, it's quite interesting also, since we have the two regimes of the sea ice influence and having the sea ice free during the summer. So it's
just
a lot
one
of
question.
data.
Are you using a long path DOAS or is it a max DOAS? Right.
Max DOAS.
Because one of the things that at least our models tell us is there's a very strong gradient. And, you know, the max DOAS, you get an average of the first few hundred meters. And within that, if you average, then you wouldn't expect to see 20 ppt for sure. But the fact that you see 5 ppt, I think that's very much, it makes sense. Because if you average across the first 300, 400 meters, you would expect 5 ppt. You wouldn't expect 20 ppt. So it could be an instrumental thing, or things have changed, which is also something, you know, would be much more exciting if it's not an instrumental thing.
Yeah, and also based on your measurements in Antarctica, you can see that every different place is just completely different.
Yeah. It's a highly heterogeneous, that's true.
Yeah,
which also shows that biology is playing a very important role. It's not just a physical emission. But
and also at Belgrano, even having the katabatic winds, we can see this higher amounts of IO compared to Marambio.
Right.
But yeah, that's all ongoing work, but it's great, all these discussions. So thanks a lot for this beautiful summary.
No, but that sounds great. I'm looking forward to reading the paper when it comes out.
Yeah, working on that. Hola. Thanks. Ciao.
Do we have more questions for Anoop before we move on to the next speaker? I'll take this as a no. Thank you again, Anoop, and just stay around for the open discussion at the end. Xu-Cheng, I think you can go ahead, share your screen and start to talk. Thank you so much.
Thank you. All right, I hope you can see the full screen.
Yeah, perfect.
Great. At first, I thank Anoop for this really nice introduction. That really saves me a lot of time, and also for the committee to invite me for this talk. And today I'm actually going to talk a little bit different. It's more about the aerosols instead of the chemistry. And I'm going to talk about how iodine and sulfur oxoacids, they could act as a very key secondary aerosol sources in the general marine and the polar atmosphere. I'd like to motivate my research by the recent IPCC report. So on the left, you can see the effective radiative forcing introduced by different components in the atmosphere, while on the right, you can see actually the estimated temperature change because of these different components. And of course, everybody knows that the greenhouse gases is heating the atmosphere, but I like you to actually focus on the magnitude we are talking about. So if we are talking about the sum of the greenhouse gases, we are roughly talking about 3 watts per square meters heating. And actually I titled this slide as the climate change, the fight with one person. And that's the reason for that is that if we are talking about the average solar radiation on a 10 years average basis, we're actually talking about 340 watts per square meter. So all the small changes we're talking about, this is roughly one person. And that actually is introducing a very large impact on the climate system already. And the second thing you must have noticed is that it shows that the SO2 is somehow cooling the climate with a very large uncertainty through a process called aerosol cloud and climate interactions. And this is something I'm going to tell you why SO2 has such kind of impact in the next slide. And the final thing that, I mean, if you actually talking about the warming effect about the greenhouse gases, I mean, this is a probability density function of that. And you can see on the greenhouse gases has a warming effect, but the uncertainty is relatively smaller. However, if you see the impact of aerosols, actually they have a cooling effect. However, their uncertainty is much larger. And that's the reason why the total anthropogenic effect is quite uncertain. You know, it can vary from roughly 1 watts per square meter to 4 watts per square meter. And the final thing that I want to talk about is actually, if you think about where this accumulated energy go, and this is also a figure from the IPCC report. So basically, it says more than 90% of the accumulated energy actually goes to the global oceans and also the ice in the polar regions. So that really leads to my motivation that I want to understand the aerosol and cloud and climate interactions over the general marine atmosphere. And as I mentioned, SO2 somehow has a cooling effect on the climate, and that is through one part of that story is through the secondary aerosol formation processes. I mean, if you think about 1 cubic centimeter air, like roughly this big, and there are 2.5 10 to the 19 molecules inside this 1 cubic centimeter there. However, there are less than 10 to 7 molecules can actually nuclei. And what I mean by nuclei is that those very few molecules can stick with each other and they can grow in size. And when they reach big enough size, they could act as the nuclei for the cloud droplets. And that has an influence on the cloud property. For example, if you have very few of those droplets, and the cloud tend to be darker, so they're going to absorb more solar radiation. While if you have more of such kind of droplets in general, the cloud tend to be whiter and they also live longer. So this way, they're going to reflect more solar radiation back to the space. And that's the reason we have to understand the cloud property if we want to project the climate change in the future. And so far, I mean, researchers mostly think that sulfuric acid, which is the oxidation product from the SO2. This is currently thought to be the most important secondary aerosol precursors in the marine atmosphere. And I'm going to introduce to you some studies that we have done about iodine and how iodine is also important in this whole game. And this study actually goes back to more than 20 years ago that a group of researchers at MESAD, Colin O'Donnell and et al., and also independently in the aerosol measurement in Tasmania, in Australia, they found that iodine are very important for the aerosol, secondary aerosol formation in the coastal regions. And the way they find it is very interesting. So in MESAD, they basically find when you have a low tide, the seaweed got exposed and you have a very strong particle formation events. While if you have a high tide, the algae got covered and you have less particle formation. And through the years, researchers found then the reason for that is because the seaweed is emitting the molecular iodine, which quickly got photolyzed and they get oxidized. And eventually, they form a lot of aerosols through those processes. And this, of course, is like the natural processes. I have a summary of all of these processes later, but also there could be some very interesting anthropogenic effect. As Russell was also talking about, for example, I'm going to show you one news post from roughly 2 years ago in the Chilean city that you can see some kind of purple cloud in the air. And of course, this purple thing is the molecular iodine. And I did some digging in, what caused such kind of weird purple cloud. And obviously, there's some kind of mining activities in the Chilean cities. They were trying to get the saltpeter and the iodine from the rocks. And somehow, during this process, basically pump failure happened during these two processes after the iodine, after the iodine plant. And basically that got the iodine emitted to the atmosphere. That's why you see such kind of purple cloud. And here I'm actually giving you a summary of these two very important species I'm talking about sulfur species. You have the natural emissions in the marine atmosphere from the dimethyl sulfide. You also have the anthropogenic SO2 emission from the ships, from the industrial activities. And the iodine species, as Anoop was talking about, and Lucy's group has done a lot of studies on this. We think the major source of the iodine species is actually from ozone deposition to the seawater. And also you have other sources, for example, through the thin sea ice. And it was also mentioned, like, what are the anthropogenic sources for iodine? Anoop has talked something about that. There's the industrial processes actually is using some iodine components. And also in the past, roughly 20 years ago, people were also hypothesizing that the soil can emit some iodine. And the source of this soil iodine could be from the marine environment in general. And also, I think around 40 years ago, people also did some study about comparing the off-road with just the vicinity of the road, the soil sample. And they find the somehow the gasoline could have a little iodine that could introduce to the concentrated iodine just next to the road. But somehow that part of the study just got stopped. Like I don't see studies anymore after that. So it's actually very interesting. I think in the future also trying to think about whether there could be some anthropogenic iodine could be contributing to the global iodine source. And I also have a reason in the later about this. And if we're talking about sulfur species, this is again from the IPCC report, the global anthropogenic SO2 is actually decreasing already. And in all of these different future projections, the SO2 is always decreasing. So when you are talking about the secondary aerosol formation from sulfur species in the future, it's almost projected it's going to be declining. And as has been mentioned already, I have to emphasize this again, these two very nice studies by Kovas and Lagrange, but also in Lucy's group as well. And basically they analyzed the ice core study from Greenland ice core and the Alpine ice core. Then both from Alfonso group and Lucy group, they found a very identical kind of conclusion. Of course, the timescale is slightly different. Basically, they concluded the atmospheric iodine has tripled since 1950. So this is really interesting because when you talk about this trend, I think this is still continuing. But of course, it's less certain how much it's going to change in the future. And they associate this kind of change to two very important things. First one is, as Anoop said, it's the increasing anthropogenic ozone. And the second one could be the thinning Arctic sea ice. And the additional thing I really want to mention here is that, before 3 years ago, when I was talking with the researchers who studies Antarctic sea ice, they were always saying that, well, there's no clear observable change that has happened in the Antarctic sea ice. However, since roughly 2-3 years ago, the Antarctic sea ice also it reaches some sort of alarming low for the 30 years. So it also starts to change. So that might also lead to more iodine emission in the future. But of course, we need to understand the magnitude. It may be small, it may be large, but whatever that's the case, we have to really try to understand that. And in this very nice summary from Lucy's recent paper, you can see the iodine emission from the sea surface, and you have a complex iodine chemistry, which Anoop has briefly touched. And my focus on this whole thing is really on the aerosol formation side, basically how iodine species can form aerosols. And by the time I roughly started this research on in 2016, and I just give you a brief summary on what was the up-to-date knowledge by then. So basically, there are two categories of species. First category was most of the researchers actually think the iodine oxides, they contribute to the iodine aerosol formation. For example, from Colin O'Dowd's paper in 2002, there was it was proposed that, for example, I2O2, HOI, and OIO species, they could be introducing the aerosols. And the later research basically proposed it could be I2O5, it could be I2O4, I2O3, or eventually in around 2013, Gomez-Martin et al. Proposed it is more likely to be I2O4. However, by that time, actually, my supervisor did a research did a measurement at Macehead Observatory with a really nice mass spectrometry method. Basically, we actually measured atmospheric iodic acid for the first time, and we found the gas phase of iodic acid was pretty high, and we think that it could be very important for aerosol formation. And my task was trying to really distinguish between these two hypotheses and to really make more evidence to see which one is the case. And the first thing that I was trying to solve was, first of all, I need to find actually a method can measure a lot of these iodine species. And this is the figure from the review paper from Alfonso et al. And just to show you how many different iodine species are in the atmosphere. And by that time, actually, a lot of these species could not be measured in the ambient atmosphere. In the laboratory environments, you can measure much more species. So that really requires something that can be really sensitive to those species. And basically, I developed this bromide chemical ionization method, and that was combined with a time-of-flight mass spectrometer from Iodine, and also basically we're trying to help to develop this in-lab with basically the company the spin-off company from our university develop this very special in-lab that could be used for the bromide chemical ionization method, because that has a very short ionization time that is very helpful for this technique. And what we could do is, essentially is that we found we could measure a lot of these different iodine species in the at low concentrations, and we claim it's a nearly comprehensive measurement of gaseous iodine. But of course, we still have a caveat here, is that we cannot handle really high relative humidity conditions, but in the laboratory with controlled relative humidity, it's really good. And the limit of detection is actually pretty low. We are talking about parts per quadrant levels, and that really satisfies our measurement in the cloud chamber. So basically, after that, we brought our instrument to this experiment at CERN, which is called the cloud experiment. So it's literally a very large metallic chamber that, as you can see in the picture, it's a large collaboration from a lot of the universities, as you can see. You may even see yours there. And you can actually see one of our convener here. This is Jane in there, and this is our instrument. And this experiment was initiated in 2017. I was there from the start. And we were basically trying to understand the aerosol formation from iodine, sulfur, and organic species. And this is just a very simple example of how we did experiments. That basically we put iodine and ozone in the chamber. And one very special thing about this chamber is that we can control the atmospheric ions in the chamber by using galactic cosmic rays and the electric field in the chamber. And basically we can independently study processes that involves the charged ions in the atmosphere and processes without involving the ions, which is neutral cluster formation processes. Since this could be very technical, our recent study actually associated those two processes to two different temperatures. So basically the charged cluster formation is very important for warm conditions, for example, the marine boundary layer, while the neutral cluster formation could be important for cold environments, for example, polar atmosphere and the free troposphere. So in the later study, I'm going to talk about these two processes in terms of the temperature, so it will be easier for you to understand. And the first thing, as I explained, is I was trying to differentiate the importance of iodine oxides with iodic acid, right? And this is for the charged cluster formation processes, which is important for the warm conditions. And as I said, I mean, most of the earlier studies was hypothesizing that it's the iodine oxide that is nucleating, but a lot of those experiments were done in laboratory conditions with a very high concentration experiment, while the field observation actually is lacking some sort of a time evolution of this cluster formation, which you can distinguish really what is nucleating. So our experiment was, I think the one advancement of our experiment was we could do this experiment at concentrations that is relevant for the atmosphere. And the process I'm trying to separate in this particular experiment I'm showing you is that we try to find this roughly 1,000 charge clusters inside 2.5 and 10 to the 19 air molecules. So that was really the challenging part, and that really requires the chamber to be very thin. And I'm showing you a time evolution of the cluster formation processes in this rainbow color. And as you can see, this purple line, the first one you see is actually the iodic acid monomer. And so we basically measure iodic acid as the initial charge cluster here. And through the time, you can see that you have the dimers form, you have the trimers form, and you have the tetramers form. And eventually we find like roughly 12 iodic acids sticking together. And the thing that we really can distinguish in our experiments is that we find all of these neighboring clusters, they actually differ by one iodic acid. And so that, of course, is saying they differ by one iodine and not two iodine. So that really gives us the confidence. So it's the sequential addition of iodic acids that is introducing this aerosol formation in the warm conditions. And also another special thing is that we do not use chemical ionization in this particular experiment. So everything happens is natural. So we do not alter the chemistry what we see in this particular figure. So that is the confidence that we think our experiment is not altered by any sort of chemical ionization. I mean, if it happens, it is a natural processes. And additionally, we also I also tried to use the genetic model to simulate these processes, as you can see by these smooth lines in the figure. And they actually agrees with the experiments pretty well. So that is really the basically the theoretical estimation actually agrees with the laboratory experiment, which is very conforming. As I said, like you have processes for warm conditions, and we were also trying to study the condition for the cold conditions. And this is a schematic of these two processes. In the panel A, actually you can see this charge cluster formation processes I just mentioned. While in the panel B, we found that, you know, if you just see those clusters, actually they have a different color, and that what this suggests is actually we observe a totally different mechanism in the for the mechanism that is important for the cold environments. We found one additional species, which is iodose acid. HL2 is actually also very important for the neutral cluster formation processes. You know, this is summarized by the schematic, but we were also trying to understand why this is the case. And we will try, of course, with the measurement by the mass spectrometers, you can see the composition, but you cannot, like, it does not tell you why this is the case. So that's the reason we try to use the quantum chemical calculation to tell us why. And I'm showing you just the 3 clusters, but we did more. So on the left, you can see the cluster of the 2 aldehyde acid HL3 dimer. In the middle, you can see the dimer of iodose acid HL2 dimer. While on the final one, you can see the heterogen dimer, which is by 1 aldehyde acid with 1 iodose acid. And we did some calculation about the free enthalpy and some estimated evaporation rate of those clusters. But I just want to show you the very final quantities that is kind of easier to understand, which is a lifetime due to evaporation. So what we find is that, you know, with the pure aldehyde acid cluster, the lifetime of this dimer is actually very short. So it's roughly 0.003 seconds. So it's really unstable. However, if you add you know, the HL2 on top of this, inside this system, you can see the cluster become much more strongly binded. They're much more stable against evaporation. So the lifetime varies from roughly 30 minutes to roughly 6 hours. So it becomes very stable, so it can nucleate in this case. Well, I mean, also one special thing is that in this one dimer of the aldehyde acid with the iodose acid, you can also see proton transfer happens from the aldehyde acid to iodose acid. So it's kind of strange in a way that we call iodose acid an acid. It somehow has a little bit of base behavior in this cluster. So that's the reason why it makes it so special. And I mean, what is the overall effect of this? You know, when we are talking about, because we always have to compare the iodine system with the sulfur system, because sulfuric acid aerosol formation is currently thought to be the most important in the marine atmosphere, right? And in this particular figure, I'm showing you the aerosol formation rate from sulfur species at 2 different temperatures: plus 10 degrees, which is a light gray, and minus 10 degree, which is a darker gray. And this is what the iodine oxoacid aerosol formation rate compared to the sulfuric acid system. So in general, we find the iodine aerosol formation rate is roughly 10 times faster than the sulfuric acid system. So that's the reason why really we have to look into this problem, and we actually have to understand the aldehyde acid concentration against sulfuric acid concentration in the ambient atmosphere, which I'm going to cover in the later slides. And of course, because of the finding of the aldehyde acid, we were also interested in finding out how it forms, because you know, it was really until very recently we got an idea on how the aldehyde acid is formed in the atmosphere. And this actually came from one observation since like 2017 in my master's thesis. Basically, I did a very simple experiment in the laboratory. So basically, I mix iodine with ozone with water, and I only use a green light. It's very specific wavelength of one component of the solar radiation, of course, and without UV. And even under such kind of conditions, I already observed the formation of iodic acid and iodose acid. So, I mean, it then took us really 6 years in really understanding what is the specific mechanism of this formation by my colleagues, Henning Finkenzeller and Siddharth Iyer, and also myself. Basically, we find I2O2 is kind of the precursor for the formation of iodic acid. And with this really realized, basically with the formation of iodic acid realized by quantum chemical calculations and our experiments, we basically built the connection, missing connection between the iodine precursor to the particles. And also with this, with the basic formation rate of the iodic acid revealed, we can actually do more simulation, trying to understand, what happens in the experiment that happened in the past, and also what is the experiment, in the cloud, and how do those experiments compare with ambient observations. And here I'm showing you one summary slide of different components on. For example, the I2 concentration, the production rate of iodine, and the IO concentration, etc. In this figure. And I'm comparing the different environments. For example, in Mahajan, that's where iodine particle formation was found. And we are also trying to compare with the open ocean through the previous studies. And also this is the one MIDO observatory, which I'm going to talk about. And we were comparing basically what's the different conditions between the cloud experiment, which I was leading, and also some of this previous flow tube experiment, what's the differences between them, right? I think I want to highlight a few parameters from this table instead of reading all of them. So the first thing I invite you to look at is actually the IO concentration in these different environments. And if you look at the open ocean in Mahajan and in open ocean conditions, we are roughly talking about roughly 1 ppt of IO in all of those conditions. And we were trying our best to simulate that, and that was actually pretty successful. The IO concentration in our experiments was also roughly around 1 ppt, as you can see the summary, while in some previous flow tube experiments, actually the IO concentration is elevated by roughly 10,000 times. So this could be the reason for this difference. And we are also trying to simulate, use the model combining all of this previous knowledge by Avanzo group and a lot of other people who are studying the iodine kinetics with this new channel we were talking about. And we were trying to see what is the ratio between these iodine oxides, IXOY, with the production rate of iodic acid in different environments. And we could do that for the MIDO observatory. We find this ratio is roughly 0.01, so which means iodic acid will be roughly 100 times higher than the iodine iodine oxides in the MIDO conditions. While for the cloud, we are roughly 0.1. And for the fluid tube conditions, I mean, the iodine oxide could be much higher than iodine oxoacids. And that's the reason we claim from those comparisons that we actually have to use atmospheric relevant concentration to study iodine aerosol formation. And then I'm trying to compare some of these field observations with the experiments we do to really build a confidence on whether our mechanism is relevant for the real atmosphere. And the first observation I'm going to talk about is actually the MIDO observatory, which I just talked about already. And this is on the Reunion Island, and this is just give you a reference where it is. This is a really nice place. I mean, this is when my flight was approaching the island. I mean, it's a volcanic island. You have a lot of beach, very beautiful beach, and a small town there, and it's a really nice place to visit. Of course, I wasn't just go there for tourism, but I also, so that's the reason I'm also going to show you some scientific results. And the very special thing about this observatory is that it's 2,160 meters above sea levels. So a lot of times it actually experienced the air masses in the free troposphere instead of the boundary layer. And actually, I'm showing you one time lapse of what I took in this observatory is that in the morning you can see that cloud is somehow rushing towards you, and that's when this air masses was changing from the free tropospheric air masses to the boundary layer air masses. And one result we revealed that, first of all, in this figure is on the x-axis is actually the IO measurement there, while on the y-axis is the production rate of gases, estimated production rate. And we were basically listing these micro observations with the cloud laboratory measurements there. And basically you can see this slope agrees with each other pretty well. But of course, the micro observatory is slightly lower in the IO concentration and in general the production rate. But we have more observations I'm going to show you that actually has higher production rate of iodic acid. Another very special thing about this is we actually measured iodine oxoacids in the free troposphere. So this process I'm talking about is not just important for the marine boundary layer. It also stands for some important for the free troposphere, for example. But of course, this is not new in terms of other iodine measurements, for example, IO and other iodine species in general. But for the iodine oxoacids, of course, you want to confirm that it is also there, right? Because the condition could be different, and the chemistry leading to the formation of iodine oxoacids could also be different, right? And the second observation I'm going to show you is actually from Andrea Baccarini's paper. Unfortunately, he cannot attend today, but this is a very important observation in the Central Arctic. So what they found was if you look at this purple versus the red lines in the panel A, basically that is showing the iodic acid concentration versus sulfuric acid concentration. So they find that in particular seasons in the Central Arctic, actually you can have much more iodic acid compared to sulfuric acid. And they found this aerosol formation event in the Central Arctic could be initiated almost solely by iodic acid, for example, in this particular case. Of course, they had a longer term of observation that I'm showing in this figure from August to September, for example. And they actually observe this clear transition but at roughly end of the summer, end of August. As you can see in the panel, the upper panel, is that you can see the iodine level. It was showed by the box plots. It's actually increasing towards the autumn. And also on the panel B, actually, you can see the aerosol number concentration. The aerosol number concentration is also increasing towards the autumn. So that really shows the clear association of the iodine with the lower temperature and with the aerosol formation in the Arctic, which makes it particularly important. In our recent study, we're trying to associate Andrea's study with the aerosol formation rate in our experiments. And this is what they observed in their experiment. Also, you can see one outlier here. I just want to mention that to be a reference. And you can see that actually the aerosol formation rate agrees, I think, reasonably well with our observations. I think we should look at the blue ones here. But of course, they don't agree perfectly. And the one reason is that for their experiments, actually, we could only derive the aerosol formation rate at 2.5 nanometers, while all this, our data is always at 1.7 nanometers. So if you actually convert that, I mean, we can't convert so easily, but it's not a surprise. For example, if this aerosol formation is at 1.7 nanometers, they're going to go roughly 100 magnitude higher. So I would say this actually is a very reasonable agreement if you're also considering this all sorts of the instrument uncertainties between their observation and our experiment. So basically, this shows that the observation happens in the Central Arctic. The mechanism probably is very likely similar to what we observed in our chamber environments. And the one additional experiment I'm going to show you is actually the observation we have done in the past years in two polluted cities in China, in Beijing and Nanjing. So this is studied by two of my mentees in China. So basically, the only thing that you want to look at is actually we were trying to observe sulfuric acid. That was the standard we were always measuring. But surprisingly, we also measure iodic acid, but mostly in the summer season. In the polluted cities, And we were trying to understand sources. However, the sources are less known at the moment because we were trying to understand this back trajectory, for example. And we see even when there's a wind from Russia, basically from the north, you still have iodine. So this points to there's some inland sources, obviously, there, because this is a daily occurrence. It's not just influenced by the marine atmosphere. So I think this is something that we can try to understand in the future. And of course, just to give you a sense of why this is important in the polluted city, we did a very simple calculation trying to understand how much iodine is helping the particle survival at the, basically between 1 to 3 nanometers. I just give you one example. For example, consider if you have 100 1 nanometer aerosols, right? And when they grow to roughly 3 nanometers, I mean, it could be possible that only 10 aerosols survive by those processes because those aerosols can be lost to wet and dry deposition, to a lot of things, and they are very fragile at that size range. And we find with the addition of iodic acid, actually you have 40% more survival probability. Basically, you could have 14 aerosols survive instead of 10. So they could have some implications for the health. But I mean, I'm not expecting this to be very large. But certainly, iodic acid could be doing something in the polluted atmosphere, which is kind of surprising to me personally, at least. But of course, previously, that as Anoop said, that we had some iodine measurement in polluted environments as well. But for the iodine oxoacids, it's probably the very first ones here. And of course, now, you know, I was talking about a few sites in general, but actually we have more observations around the globe, as which is summarized in this particular figure. All these sites I mentioned are inside of those figures, and we have, I'm showing you 10 different sites. I've been to roughly 6 of them, and then you can see that actually in the polar regions and also in the coastal regions, you have much more iodine in general compared to, for example, the urban regions and also in the Reunion Island. So basically that suggests the iodine aerosol formation could be more important for the general polar and the coastal region, but also they could have an implication for the general open ocean environments, as I'm showing you some calculations. And now you must have been thinking, okay, you actually have both the iodine and sulfur species together in the marine atmosphere, right? So what do they do? You know, when they meet each other, is the aerosol formation somehow independent? Do they just form aerosols independently? So this is the 1 + 1 = 2 problem, or is there some synergy? And our results actually shows there is a very strong synergy. And in this particular figure, I'm showing you the aerosol formation rate from sulfuric acid again as a reference. And this is what's gonna happen if you add iodine you know, inside this sulfur system. So in general, you can see the aerosol formation can be enhanced by roughly 100 times, which is very significant in this particular case. In basically all of this data we explored. And then, of course, we are trying to understand what is the mechanism behind this enhancement, and also we want to see whether there's a true synergy by observing the aerosol basically charge cluster composition. And in this figure, this is a mass effect plot. You don't need to understand the details of what is a mass effect plot, for example, but you can just see like one dot, one marker in this plot actually shows one species. And currently I'm showing you the iodine species, which is the colored purple, and the sulfur species, which is colored red. And actually in this particular experiment, we also observed the mixture of iodine with sulfur species, which is marked as blue. And once you add ammonia inside this system, which is additional species that is important for aerosol formation, you can see actually sulfuric acid and ammonia, they're gonna nucleate together. But actually you don't see iodine with ammonia because iodine aerosol formation is already very fast. It actually doesn't require ammonia to help its aerosol formation. However, finally, you're gonna see all of them together. So basically you see iodine, sulfur, and ammonia together inside those clusters. So what this really suggests is that all of those components, they work together to promote the aerosol formation in the general marine atmosphere. And we associate again, basically with other analysis, we can associate basically which iodine species is important for what kind of environments. And we found iodic acid is important for the warm environments because iodic acid enhances sulfuric acid charge cluster formation processes. While in the cold environments, it is again HIO2. It actually enhances the aerosol formation from both iodic acid and sulfuric acid. So, so with this two distinct mechanisms, and that's the reason why you see this kind of very strong enhancement. And we were also trying to constrain our observed aerosol formation rate by different components. The panel A was exactly the same figure with what you just saw as I was presenting you, because this is trying to constrain the aerosol formation rate by sulfuric acid alone. And in the middle, I'm trying to constrain the aerosol formation rate by both the iodic acid and sulfuric acid. And you can still see that actually there's still a large difference between the observation with the prediction, theoretical prediction. While if you eventually put all of these three components together, the aerosol formation rate got constrained. So they really gave us some hope that we can eventually constrain this aerosol formation, which eventually can be used for global climate models to predict aerosol formation from our experimental results, for example, which I'm currently working on. And finally, I'm trying to, again, associate our observation with the ambient observations. And as you can see in the panel A, it's actually it's a summary of all of these different observations from different ambient observation from the Arctic to Antarctica. And this value is actually ratio between iodic acid with sulfuric acid. And you can see, I mean, the current view actually thinks that sulfuric acid has a larger concentration compared to iodic acid, while iodine oxoacids is not important. It's only important in the regional scale, but not global scale. However, our summary actually says these two acids, their concentration are actually pretty comparable. And we're also trying to understand the enhancement because of iodine. On top of the sulfur system in the panel B, this is derived from our experiment. I'm just going to highlight one specific point here, for example. On this point actually shows iodic acid to sulfuric acid ratio as 0.1. And in our experiment, we observed the aerosol formation enhancement is 30 times. And this is not 30%, this is 30 times. So this is really significant. And if you look at vertically, compare this ratio, for example, with ambient observation, you actually see that most of the conditions in the ambient observation actually is higher than 0.2, this ratio. So what this really says is that our results shows, so first of all, these two acids, their concentration comparable. And our results also shows, even if iodic acid is 10 times lower than sulfuric acid, iodine oxoacids is still critical. So in general, the iodine could enhance the sulfur nucleation by at least 10 times globally. And it actually could have a very strong indication for the general open ocean conditions, which I think still needs to be confirmed by ambient observations. And this will give you a general summary of what I'm really talking about in this whole discussion. What is their climate relevance inside these discussions. And I'm showing you actually the aerosol sources, what people think is happening in the global atmosphere. And this is, I'm showing you a summary of this temperature prediction by the end of this century by 40 different Earth system models, which only include the sulfur species I'm going to show you. Actually, it has a really large uncertainty. For example, some model is predicting there are going to be 2 degrees warming, while some model is predicting there could be 6 degrees warming. And actually constraining that is very difficult. And one part of that, as I already showed you at the beginning, the aerosol cloud and climate interaction is very uncertain in the current climate projection. And that's the reason why we have to include additional processes, as I was mentioning, for example, because the iodine species is actually forming aerosols together with the sulfur species. And you might be thinking, if you relate to what I was talking about at the beginning, if you have more aerosols, you're going to have brighter clouds, right? Does it mean that the climate projection is going to predict a cooler future? Actually, that's not as simple, because all of those climate projection actually has a reference, which is the pre-industrial era. and I'm just going to show you. So if you compare the future projection with the prediction of the pre-industrial era, you're going to derive this temperature change, right? So the decreasing SO2 trend in the climate model is actually already included. So that's not something I'm going to talk about. But as I mentioned already at the beginning, or in Anoop's presentation, actually we have increasing iodine concentration in general. So what's my projection for that is that in the pre-industrial, in the current, in the future, it's probably going to introduce some cooling effects throughout just by aerosols. And it's possible that in the pre-industrial era, you're going to have less cooling effect because the iodine concentration was lower. While in the current and in the future, you could have potentially stronger cooling. So which may suggest from the aerosol, there's going to be some cooling effect as well. But this is something that I think we have to include iodine aerosol formation in the climate models so we can really derive a more certain conclusion. And with that, actually, I want to acknowledge all of these results that was done with a huge collaboration in the cloud community. And also all of my results I'm presenting today was done at University of Helsinki. And I also take this chance to thank my current host at University of Cambridge for hosting me. And thank you for your attention.
Okay.
And I'm happy for any questions.
Yeah. Great talk, and thank you very much, Xu-Cheng, for this interesting results on, especially on this synergy effects of iodine and sulfur on the nucleations and aerosol formations. Okay, now we are open for questions to Xu-Cheng. Yeah, anyone have any questions? Yeah, Lucy, please go ahead.
Okay, yeah, I remembered to unmute this time. Yeah, maybe this is a question both to you, Xu-Cheng, which is a lovely talk. Thank you. Really amazing work you've been doing, and amazing to see this progression of the science here on the aerosol formation. But maybe it's back to Anoop as well, because I'm pretty sure Anoop, is it right that in Alfonso's and your recent Nature paper you had an aerosol warming effect?
Yes, but that wasn't through the IOPs. It was through SOA effects.
It was through So do you want to just explain that was more chlorine chemistry, or?
That's more chlorine chemistry, yeah. So very little iodine chemistry, and also the change in Hawkes affects SOA formation. So that reduces the SOA concentrations. So it's that dual effect.
Yeah, so that's interesting what the overall effect is. There's the IOPs, but you had the IOPs in that model as well, right? It's just what the overall
yeah, so at least in that model that there was IOPs. Of course, it's not the same mechanism. So the overall effect of IOPs was minor. It basically showed that it didn't have an effect at all. Now, if the enhancement is so much higher, then yeah, it's definitely worth quantifying to try and identify.
Yeah, presumably you didn't have these synergistic effects that Xu-Cheng is suggesting.
Yeah,
right.
No, we did not have
that.
Yeah,
yeah. So really nice to see. Xu-Cheng, I'm just wondering back to you, what kind of observations do you think we should be making to to really improve on this understanding?
Yeah, I think your site is actually very important. Cape Verde, that's in the tropics. I think, well, okay, I'm not sharing anymore. I want to go back to the observation I'm showing. Can you see my slide again?
Sure, yeah.
Right, sure. Actually, I want to, if you look at this slide, if you look at the observations, I mean, actually in the paper version, actually I have a gap, which is highlighting the 30 degrees north. And if you look at all of those observations, they're actually mostly mid-latitudes and to high latitudes. So I think the very important thing is actually what is missing, as Anoop was also highlighting, actually we need to do more observation in the tropics. Not anymore in the, well, in the Arctic polar regions, of course, we want to understand more. But I think in terms of iodine aerosol formation, what is more urgent is actually in the tropics, because all of your sources studies actually is suggesting the tropics is has much more iodine in general, right? But we don't have actually the mass spectrometry data in those regions. You have like a lot of observation about IO, etc. But for the direct aerosol precursor, I think this is something that is missing. And the second thing, I think what is important is actually the vertical profiling. For example, the farm aircraft measurement. I think that would be important because I think a lot of the previous research was done, which was done in the marine boundary layer, to actually find the aerosol formation in the open ocean boundary layer was pretty rare. However, if you actually go to the free troposphere, actually there are a lot of aerosol formation happen there. And actually that is consistent with our laboratory experiments as well. Because we find, for example, if you compare the aerosol formation at 10 degrees with the aerosol formation at -10 degrees, actually they differ by roughly 100 times. So just by going, vertically by a few kilometers above, you might find this condition very important or very optimal for the aerosol formation. And I think those are the two areas I can think of for the ambient observation.
Thanks. That's good to know.
Yeah, okay. Any more questions? Yeah, Anoop.
Yeah, Xu-Cheng, very nice talk. Very interesting to see that there's a lot of potential for iodine to actually affect aerosol formation. I had a question about your slide number 12, where you see the sequence of growth, the growth of clusters, through your CERN experiments. What you said was the difference between the cluster sizes is 1 HIO3, right?
Right. Sorry, I'm going there.
Sure.
A sec. Right here.
That rainbow plot. So the difference is 1 HIO3. I was wondering why you don't get coagulation between the clusters. So it seems to be very linearly progressing. You need every time you just add an HIO3. But why doesn't cluster number 5 coagulate with cluster number 7, for example?
Right. That's actually a very unique thing about our experiment is that we can keep the chamber to be extremely clean. So that's the reason that you can see, this whole experiment having a very clean stuff. Basically, at the starting point of this experiment, we don't have large aerosols at all. And that's the one why you don't have we don't have a very large coagulation thing in the chamber. And the second thing to this is actually all those lines you see is actually negatively charged. And they cannot, their correlation rate with another cluster, which is negatively charged, is very slow. It almost doesn't happen in the time scale we are talking about in the chamber. So those clusters you see, they will not stick with each other. And the only way they can grow is actually by colliding with the other neutral molecules. And the dominant one is iodic acid.
Okay, thanks.
Right.
Okay, Hélène.
Yeah, it's actually on the same slide. Here you mentioned warm conditions and later on you talk about cold conditions. I was wondering, well, what's your definition of warm and cold? Do you have a range of temperature?
Yeah, so this is, I would say it's very arbitrary. I should have mentioned that the warm is above 0, while the cold is below 0. So I just want to make it simple so it's easier for you to understand. But it's not like the warm in a sense of a human body, for example. I really should have mentioned that. Yeah.
Okay, so warm condition could be relevant for high latitudes as well, around 0 degrees.
Oh, definitely. Yes.
Okay.
That's correct. Right. Yeah.
Okay.
And I think that's probably important for Andreas, this observation in the Arctic, for example. This is actually, if you look at, it doesn't, it does have a temperature. So sometimes it could be at roughly 0 degrees. Yeah.
Yeah, any more questions? Isolate. Go ahead.
Hey, thanks for the great talk. You mentioned that the IOPs, like the HOIs, are also important in the anthropogenic environment, so like in Beijing. Do you have an idea of the sources there? you thought about this?
Oh,
Would
yeah.
this be cycling?
Yeah, I was briefly touching that. Well, if you just ask my hypothesis, I think that one thing is in general, the soil and the vegetation could be a source. I mean, but of course they are not that large. But actually, there was some study. I think it's by Seif et al., if I'm not mistaken. Basically, they did some sort of aircraft measurements over the U.S. and they found like the CH3I emission from the inland, like U.S., could be it's comparable in terms of per square meter, for example, is comparable to the marine atmosphere. So I think the vegetation in the soil in general could be a source. And the second source, potential source, could be anthropogenic sources, which are by vehicles, for example. But I think that part is not well quantified, and I don't want to claim anything like from that. But I just want to mention, actually, the iodic acid concentration we measured in the summer is the maximum, daily maximum is a few E6. It can be roughly 3 E6. This is actually comparable to the ones we measured in Reunion Island in the free troposphere. So it's actually not a low concentration we are talking about. It's pretty comparable to the open ocean conditions, except the tropics. So I think that's really the surprising part. Actually, we are still trying to understand what are the sources, but currently we don't have a clear idea.
Thank you.
Thank you.
Okay. Yeah. Any other questions? More questions for Xu-Cheng? Yeah. No. Then yeah. Hélène.
Yeah, it's actually not direct. It's not for Xu-Cheng. It was my question relates
General.
to the marine side of the cycle. So in the two presentations, the Anoop and Xu-Cheng explained that with increasing ozone concentrations, we have more ozone deposition to the ocean. So this could this could lead to increased emissions of iodine, if I got it right. I'm wondering if, based on what's occurring and what we know is happening in the surface microlayer, if there's anything else that could change in the coming years, coming decades, that could increase or decrease iodine emissions. It's very naive questions because I know nothing about all of this. I'm just wondering if anyone in the audience is investigating such processes in the surface microlayer. Yeah, Rosie, go ahead.
Yeah, I'll see.
Oh, yeah. I've sort of jumped in, but if anyone else wants to say on this, I mean, that is some of the work that we've been doing recently that I mentioned before we got started, and in terms of how the actual ocean iodide fields might alter, because we have ideas that they could be changed by other aspects of global change. For example, increasing ocean deoxygenation might change that distribution because it's redox sensitive. Changes in the biological productivity of the ocean will certainly expect to change it because the production of iodine in the ocean is related to that. Also, changes in ocean circulation will change it. And also things like ocean acidification may impact the biogeochemical processes. So there's actually quite a few big global change things that we think could change the sea surface iodide fields. And that's some of the modeling work that we're sort of trying to do, but there's a lot of uncertainty with that. And then other modeling work to sort of really test the sensitivity of the iodine flux to those changes, because that may, they may not actually be large enough to have an impact. That's something that we sort of really need to look at. So there are things that could change the iodine fields, as well as we've heard in the two speakers, changes to anthropogenic ozone levels, or the ozone levels that then change the flux as well. That'd be my comment on that, if that helps answer it.
Yeah, I think that's a very good answer, isn't it?
Yeah.
Very comprehensive. Also keep in mind that we're also changing the macroalgae distribution. So, those things might also affect it.
Yeah, I think I very agree with Anoop, this microalgae, especially this cultivated one that you mentioned. And think this will totally change this iodine emissions. And I also very agree with Xu-Cheng's that we should have more this measurement in the tropics area, tropicals. Yeah.
Yeah.
Okay.
Actually,
Yeah.
just next to that, actually, I have a question for the your group in general. So, are there some plans? Because I think you've got the mass spectrometers. Of course, the chemical ionization inlet is slightly different, and you know, I know there could be pros and cons. Anyway, we can discuss that offline.
Yeah.
What is York's plan in contributing to this? For example, associated with Cape Verde observation, when do you plan to, have you already done that? And what is your plan for deploying your mass spectrometers in the tropics?
Yeah, no, I mean, it's a really good suggestion to go down there. At the moment, I think as we discussed, you know, yeah, we have a mass spectrometer now. Our immediate plans are to do some gas exchange work, looking at these questions of how Hélène just brought up just then about the organics and how they impact both I2 and HOI emissions, because we've not done this yet on HOI emissions, and now we have the capability to do that. So in fact, we're partnering with a group from Heriot-Watt. So they've built this gas exchange tank. We can actually look at also more in depth about how wind speed and how turbulence impacts the emissions, and possibly also working with Manabu Shirara on the modeling of how these organic layers, you know, affect basically the multi-layer of all of these different emissions. So that's the emission side. We haven't, I mean, there are sort of potential plans to go to Cape Verde with the instrument. I mean, in principle, we can sort of do that at any time now. It would be nice to coordinate with others. And so if you guys were interested in doing sort of more iodine measurements on iodic acid, we should talk about this offline. And I'm sure there'd be ways that we could, you know, some funding that we could find or something. But yes, it would be really nice to get more of a picture. Obviously, we know from Anoop's measurements of IO, all those years ago, and with John's plane that the iodine exists there. Yes, as you say, it's a place in general in the tropics where iodine emissions are higher. Although I don't know if you've just seen our recent paper on the iodide and ozone rate coefficient, which basically kind of drops
one order of magnitude.
It drops the tropical emissions down, the sea surface emissions down by a small amount. The bigger effect is that it ups the, I mean, this is in Ryan's ACP. The bigger impact is that it increases the emissions in the higher latitudes, the polar regions. So lots of questions, but yeah, let's talk about how we can do some of that.
Yeah. I agree with you, Lucy. I think I talked to you in Iju last week.
Yeah. No, we're looking forward
quite
to
interesting. Yes. Because about this wave tank, I told you that we also have, but I think there are lots to work on it in the wave tank. I think we should also discuss it offline. Sure, what we can do with that. Yeah. Maybe probably. Yeah.
Sorry, I have a question to your group, Anoop, or general to you about the sources. So, I mean, we were talking about the basically it's tripled since 1950s around. So, up to your like most updated knowledge about everything, let's say, you know, cannot be everything, but what will be your projection for the future? You know, especially we're talking about by the end of this century. So what, you know, do you think, first of all, do you think it will be continuing increasing, and what kind of magnitude we are talking about? Grand challenge.
Well, this all depends on the RCPs, doesn't it? And what methane future holds. You know, all the projections are climate change is as bad as we think it's going to be. So, you know, if methane continues to rise, then we're going to end up with a higher ozone. So this is like climate. We need sort of ESRES people there to really look into their crystal ball. But yeah, I don't know if Anoop, you've got any thoughts on that?
Yeah, no, pretty much the same thing. It really depends on the scenario that we follow. But I mean, considering how things are going, one would expect it to just keep on increasing, right? There's no indication that it's reducing right now. So yeah, the inorganic emissions, definitely you can think about them as increasing. The organics, I don't know if we have some good ideas about that. Right now we use fairly static emissions.
Yeah, I mean, that's an area still that we should probably work on and improve at some point. You know, there's a bit more data out there, and you know, yeah, the climatology seems to work, and that, you know, that's out there, but it's not quite right.
Yes.
Yeah, but you know, this is maybe more of a second order priority, but
Yeah, I wonder if we can use newer techniques to think about more dynamic emissions as compared to using just climatologies. Might be worth doing.
I think that's a good point. Definitely. Yeah. Yeah.
Yeah.
Xu-Cheng, one of the things I was wondering about in your mechanisms, does the photolysis of any of these clusters play a role? Are they photoactive, or?
I think I think those parts are actually not well studied. First of all, I mean, there were some studies, some calculations, I think by Alfonso's group, I guess. I should remember that.
Not for the
for the
HIO3,
aldehyde acid,
if I remember.
yeah, for
No,
HIO,
just for
not
HIO3, yes, but not for the clusters,
Yeah.
right?
Yeah, exactly. For the clusters, is less answer. It's less certain. For HIO3, it's pretty stable, I guess. And for this, actually, I was trying to look at these dimers like HIO3 with HIO2 at Mahajan, and those ratios are actually pretty comparable to our experiments. So I think it may happen, but it's probably not at a so significant rate, at least compared to the aerosol formation, maybe. But yeah, but it's good to study this.
No, considering the impacts, I'm looking forward to your results from, putting it into a larger model. It will be very interesting to see whether it matters or not, right?
Yeah, definitely. I can just I'm actually now working on the parameterization for whoever is interested, but it's from the cloud experimental data. So it's just not just from theoretical data. I can say, like, if you're interested, by the end of next year, probably there will be some iodine parameterization that all the models should be able to adopt. And I'm also thinking that there should be more models doing that, not just my model. So that would be cool.
Yeah, actually, that's one of the largest uncertainties we have about even the gas phase thing. We need more models to do this. Right now, it's just a couple of models which have that. Would be really useful to do maybe like a multi-model estimation of this in terms of all the effects, not just in terms of aerosols.
From what I know, actually, there will be several models. Like I'm working on the UK resistant model, which Ryan Hosseini is working on. And there will be the German model, EMAC, and there will be the European model, EC Earth. Those three models are inside the cloud consortium, and I know they're going to be putting iodine in. So we have a bright future, hopefully. And also the emissions, whenever we get better one, then, there's this whole chunk, chemistry, emission, the aerosol formation. So should be, I think we have a large space to improve in the future.
Right, so no more questions?
Sounds really good.
Yeah, is there any more to comments or questions?
This is your last chance for questions.
Yeah.
Well, if there are no questions, I'd like to thank again our two speakers for two amazing presentations, and everyone in the audience for the discussion that followed. And the seminar was recorded, so if I know I have a bunch of colleagues that couldn't attend the meeting today, but we'll circulate the link to the recording, so you can get that information as well.
Yeah, and hope in future that the CATCH and SOLAS can have more interesting topics for this webinar in future, and invite more interesting scientists for the presentations. Yeah. So yeah, thank you very much again to Anoop and Xu-Cheng and all these people that contribute to the discussions. Thank you very much.
Thank you.
And thank you guys
Thank
for
you, guys.
organizing
Thank
this.
you.
It was very well
Yeah.
done and very smoothly done. Cheers. Thanks a lot.
Yeah, exactly.
And nice to
Thank
see
you.
everyone
Yeah.
again.
Yeah, happy to see everyone.
Bye-bye.
See you guys.